So good morning and welcome to another lecture. You may be hearing a couple of scraping noises in the background. It's because there is some reconstruction going on at my neighbors. I've already called there. They promised to be silent until 12:30, so let's hope and wait. This morning it was really loud drilling, so I hope it's going to be okay like that. So another lecture, and I have seen that there have been a couple of new questions on Canvas. So I would like to start today with answering the questions that are currently on Canvas. And then I'll do a very short recap of what we have seen on Monday with the looking for extrema of functions, looking for maximum, minimum, and so on. And then I would like to move to the next topic, which is inverse functions and stuff we can say about that. But more about that later on. So first of all, let's switch to the Canvas site. And that should be here. Yep, there we are. So here are the questions of week B. And as I told you last time, I started a new round of questions. So in principle, all the questions that you will see here are new. So let's see. The first question, well, as you may have seen, you can upvote, downvote them. That's not used an awful lot yet. But they, and otherwise they appear in order of newest first and going to oldest ones. So here is a question from Zainab, and he asks something about 35 in the book. So this is a question still related on vectors. Let me switch to the question. I already prepared this, so we can have a look here. So this is the question in the book. It's question 35 from chapter 10, section 1. So let me add that here already. So this is section 10.1. 10.1. And so we are given two vectors, A and B, and a vector C. And the question is a bit tricky. Let's first read the question. So it says sketch A, B, and C. Okay, that's fine with initial points at the origin. I'm sure you can do that. And then sketch a parallelogram with diagonal C and sides parallel to A and B to write C in the form some constant times A plus some constant time B. So what's happening here? Well, I'm just going to sketch them. So I'm not really drawing the vectors as they should be, but we have a vector A. We have a vector B. And then given is a third vector, which is a lot bigger. Let's say something like this, C. And now basically what the question is that we want to construct a parallelogram. And as you hopefully recall, that's like a rectangle that you give a kick and then it's slightly distorted and the angles are not 90 degrees anymore. But the important characterization of a parallelogram is that if you take two sides, that they should be parallel. So you have two sides like this and two sides, for instance, like this. So the two opposite sides are parallel to each other. And now what we want here, so let's do that in green today, is we want to construct a parallelogram. The sides should be parallel to A and B. And it should have the diagonal C. So basically what you should do is you should extend this vector A and extend this vector B. And then you should have a line parallel to how A is going up here. And a line parallel to the vector B, so that's something like this, also going through the point where C is pointing. And then the parallelogram that's being meant in the question is the black one that I'm currently drawing. So that is just understanding the question. So what are they asking here? actually solving it is a lot easier, because what they're asking is to write some constant times A plus some constant times B should equal C. So this is really in mathematics the question. And C1 and C2 are two numbers. So what are the values of these numbers? How can we write C as a combination of A and B, as a linear combination, it is called, of A and B? So let's just plug in the values. So we have C1 to 1 plus C2 1 3 equals 7 11. And if the C1 and C2 confused you because there was also a vector C, I fully understand that. The notation is not great here. So it would have been better to use different symbols for C1 and C2. So if you write this is what we have here, this here, in what I'm highlighting now. It is basically a vector equation, and you can write it in terms of the components. And if I do that, then we have 2 times C1 plus C2 equals 7. And we have C1 plus 3 times C2 equals 11. And probably you know how to do this. So let's quickly do it. So from this equation, we find that C2 equals 7 minus 2 C1. I can substitute that into the second equation. So then we find from these two that C1 plus 3 times C2, so that becomes 21 minus 6 C1 should equal 11. So we have minus 5 C1 should equal minus 10, and we find that C1 equals 2, and then apparently C2, well, that's 7 minus 2 C1, so that's 7 minus 4, and that equals 3. So apparently, so the conclusion is, basically we're done now, but let's write that down. The conclusion is that C1, which is 2 times A plus 3 times B equals C. And of course you can easily check that, right? Because if you look what it says here, that is the same equation. But if you now plug in C1 equals 2 and C2 equals 3, it should hold. And you can easily see that this is true. So this is what was being asked here. And maybe it was a little bit confusing, but you see that actually the computations, etc., they're not that difficult. So with these questions from chapter 10, I think the most important thing is trying to understand what's happening there. What is actually being asked. Okay. So let's go to the questions again. They are here. And then I'm going to scroll a little bit. So how do we solve? We've just done question 35. Then the next question, also from Zeynep, is how do we evaluate the limit, blah, blah, blah. In my book, on my iPad here, I have the 4th edition, but the question is different. And this question is not a very interesting one in the sense that what is being asked here, so I will shortly address it, but I don't think it's a very nice question. So if I read it correctly, we're being asked for the limit of x is going to 0 from the right, the ln of x times the sine of x. Please correct me if this is not what is actually being asked, but as I said, question 14 is different in my book. Now, the limit of x going to 0, it is from above, since the logarithm needs to have a positive argument. If you would just put this, you would find 0. If you would find this, you would also have 0. And then we have already seen that the product is also 0. So basically what we have is that we could also write this as the limit y is going to 0 ln y. So I can rewrite it like that, because if x is going to 0, then y is going to 0. Now, if you recall quickly, x-axis, y-axis, y is ln x, this is at 1, then you immediately see that if y goes to 0, then we're basically going here along the graph, and we see, sorry about that, I should have switched to my iPad again. There is a bit of a delay, as you now see in me talking on YouTube and you in the chat room. I can shorten that delay, but I'm not sure if that's going to work out. I'll try that next time. It's a setting in YouTube. But quickly, we now have the limit where we are walking along the red graph. And as you can see, this limit is going to be minus infinity. So, as you see, the limit does not exist, is one way of putting it. Some people say it does exist, but the value is minus infinity. Our current textbook says the limit does not exist, and as a kind of additional information to that, it equals minus infinity. So if you would like to draw the graph, then you know that you have to draw it like this, going to minus infinity. Okay, so that was the question, the other question from Zeynep. Okie-do. So I am switching back to the questions, and hopefully I don't forget to switch back to my iPad. Next. So the next question here is from Jana, and she says, I'm often confused what I have to do when I have to compute a limit, because there are a lot of options. Is there a step-by-step plan I can follow? So I did look at that, and I'm going to switch to my iPad again. And I have stolen this from my colleague who teaches for industrial engineering, so that's the Calculus Variant 2, but he made this kind of recipe. So this is due to Michiel Hoogstenbach, and I made a screenshot from his presentation there. So here is a kind of checklist what you can do if you encounter a limit. So the first thing is always just to try to substitute x equals 0. So if you have a limit, x going to 0, just plug in x equals 0, see if you find a number. If you find a number, you're done. That's great. Of course, the limits that we will be asking you during the test probably won't be as simple as that. So the next option you could have is that you have something that is unequal to 0 in the numerator, and then you're dividing by 0, so the denominator is going to 0. So then it might be interesting to consider the two separate cases, whether you come from the right or whether you come from the left. And if both of these are infinity, then the limit is infinity. And as you can see, for Calculus Variant 2, they use a different textbook. So there you could already have that. They say that the limit does not exist or does exist or whatever. So our textbook says the limit does not exist. And as a bit of additional information, we find that the limit goes to infinity. If both these limits, so this limit and this limit, if both of them go to minus infinity, then the limit goes to minus infinity. And if you find one of them to be infinity, the other minus infinity, then the limit does not exist, and you would have something as we have seen. So here, for instance, you could have that you have a function that has a vertical asymptote, and it does something and it goes to minus infinity, and then it comes back from the other side. So that would be the type of function that you have then in this situation. Next, if you have 0 over 0, you might try L'Hopital's theorem. So we didn't cover that yet, but we will. So that's something that we will encounter later on during the lectures. Taylor, we don't do, so that's variant 2 only. Or divide out a factor. So divide out a factor, what does that mean? It means something like the limit x is going to 2, x minus 2, x squared minus 4. So there you can write this thing as x plus 2, x minus 2, and then you can divide out the x minus 2 and still compute the limit. So that's what's being meant there. If you have infinity over infinity, either dividing by the largest exponent or whatever, the largest term in the denominator, so we've already seen that trick, we already covered that, or you could try L'Hopital as soon as we have encountered that. If you have something that oscillates, so what oscillates mean is what the sine and the cosine do, so they go between -1 and +1, that's what oscillating means. So if you have something that is oscillating over something that is infinite, you will find 0 and you should use the squeeze theorem. So if it oscillates, it goes between a lower and an upper value, and then you can have a squeeze theorem, which are the lower and the upper boundary, and then you can compute the limit. If you have something that is of the type infinity minus infinity, you should try to combine them, try to group them together, so rewrite them algebraically. Then 0 times infinity, we don't know what that is, right? So that can be any number. So you can either write it as 0 over 0 or infinity over infinity, and then basically you're back into cases 3 or 4. And this we will encounter later on. So I'm not going to spend a lot of time on that, but we will see this trick later. And then as a kind of extra, it says here, if you have 0 over infinity, that's 0. You don't have to think about that. Also 0 to the power infinity, that's 0. Infinity to the power infinity, that's always infinity. So these are not problematic, and you can write down the value. So hopefully that helps, and that answers Jana's question. Okay, so I'm going back to the questions now. So if you have to compute a limit for which you see it is going to infinity or minus infinity, can you just write it immediately, or do you have to show certain steps? It depends a little. If you can see it immediately, you don't have to write any steps. So if you have 1 over x and x is going to 0, you can immediately write down that it's plus or minus infinity depending on how you go to 0. If you cannot immediately see what's happening there, you should elaborate or explain. Sometimes you can do that in words, sometimes you have to rewrite a little bit algebraically. This one is also interesting. When you're asked to compute the derivative of, for example, horrible function, is it sufficient to write this as horrible function again? Or is it better to simplify this as a single fraction? Depends. If you just want to know what the value of this thing is for x equals 1, then you don't rewrite it. You just plug in x equals 1, because that's easiest. If you would have to differentiate once more, then probably it would pay off to write it as a single fraction. So if you're going to use it again or more, or if it's a final answer, if it said give us the derivative in its nicest form or something like that, then you would have to do the rewriting. But as an intermediate step, it depends on what you will be doing with it. So here it says, in the book they sometimes use things like, and then square brackets. So square brackets can be used like normal parentheses, like normal round parentheses. Sometimes when you have a bit of a longer expression where you have many parentheses, it's helpful to have square brackets too, just to make clear where they start and end and stuff like that. So they can be used as kind of alternative, just to make it a little bit more clear to read. It can also be, so when we talk about integration is one of the next topics that we will be talking about. When we do that, then often with integration you also use them if you have found a primitive function, as you may recall from high school. So you either write a vertical bar or you write these square brackets. Now, this question, so in the book they say that, let's just read the normal square root function, square root of x is continuous for x bigger than 0 when n is even. Why is it not continuous? Well, basically the question is for x equals 0. Now, this question is more tricky than you probably think. The reason is, if you look in the book, let me quickly switch to where it is in the book. I'm going to switch screens in a sec. You don't have to tell me now. I know you cannot see it yet. So that would be, I'm scrolling to the definition of continuity in the book. So now I'm going to switch to my screen, which should be here. Ooh, that's a bit small. Can I make that bigger? Probably can. That's already bigger. And that's great. So here you see the definition that the book uses for continuity. And in particular, it says a function f defined on an open interval containing x equals a. Now, that is one possible definition, and there are other definitions. But because the book uses this definition, then if you look at the square root function, so the normal square root function, so we have x-axis, y-axis, y equals square root of x. The problem that the book has is that it cannot give an open interval. So basically you're looking for C and D such that C less than 0 less than D, because then we have 0 is in the open interval C, D. You cannot do that now, because the square root function is not defined for negative values. We cannot find such an open interval. So the book cannot use its own definition. Now probably you'll understand that here in this particular situation, you shouldn't look at the general limit here, but you should look at a one-sided limit. So what you should really do if you want to talk about something like the square root function is require that the limit of x going to 0 from the right, square root of x, equals 0 equals square root of 0. So yes, the square root function is continuous, but the book doesn't say, because the definition doesn't allow it. If you think this discussion is too technical, it is too technical. You don't have to be able to reproduce this or anything. Hopefully you understand more or less what's going on, but the book is kind of bitten in its tail by its own limited definition here. So yes, the square root function is continuous at equals 0. That's the main message. But the discussion requires a bit more mathematics than the book offers. Okay. Going back to the questions. It is already clear, that's great. So Fenna replies to her own question. And actually we discussed a little bit about vertical asymptotes too. And then I started recording a new round of questions, which is great. So we have covered these, and that means that I am going to scroll to the top. and I've got a bit more options now than you have. So what I'm going to do here is start indeed again a new round of questions. So I'm going to click here and I am going to confirm that I want a new round of questions. Okie doke. And all the questions are gone. So as you see, I spent quite a bit of time on this. We're 25 minutes into the lecture. I'm perfectly happy with that. So if you have further questions, just put them here, put them in the questions of the week, and I'll go through them again on Monday. I'll happily do so. So for now, let's go to the material for this week. And I am going to go to the slides again. Okie doke. So here we are. So what we will cover this week, and now I'm going to change my screen again a little bit so that you have a full screen, hopefully. I know you don't have it yet. 1 second. This one, that's better. Okay, so here we are. Great. So what do we have? I have to change my setup here a little bit. Yep. Okay. So on Monday, we have been talking about derivatives, about maximum and minimum, and about first derivative tests, stuff like that. So going through that in a nutshell, what we have seen is how you can find maximum and minimum of a function. So we have global maximum, local maximum. We've seen the difference there. And we've also seen how you can find them in general, given y is f of x. You have the expression for the function x. So if you have that it's given on an interval and the endpoints of the interval are part of it, then to find the global maximum and the global minimum, what you do is a couple of steps. So you look at the critical points. That's the first main idea. So you compute the derivative, you find out where it equals 0 or where it is undefined. You make a sign chart. And for global maximum minimum, you don't need a sign chart. Sorry, I was running ahead for the local extreme already. So you compute the value of your function. You compute the function at the two endpoints, because if you're on a fixed interval, they could also be a maximum or minimum. So how can you see that? Well, easily if you have a function like y is e to the power x, and if you would restrict it to a certain interval a, b, then you see that the minimum is at the left and the maximum is at the right. And the derivative is defined everywhere, but it never becomes 0. There are no critical points here. So for such a situation here, if we have a situation like this, then the extrema, minimum, maximum are at the endpoints. And basically the largest function value, so you compute f at those points. The biggest one is the maximum, smallest one is the minimum. So that's how it works if you want to have just global maximum, global minimum, one value. Then we have also been looking a little bit at increasing, so going up and decreasing, going down functions. The first situation is if the first derivative is positive, here the first derivative is negative. And based on that, we have the first derivative test. So if you have given a function f on an interval, and if you know it's a nice function in the sense that it's differentiable, you can differentiate it and the derivative is still a nice function, continuous, stuff like that. And if you have a point where the derivative equals 0, then you know how you can check whether it's maximum, minimum, or inflection point. So if the first derivative goes from plus to minus, it is a maximum. If it goes from minus to plus, it is a minimum. And if it does not change sign, then there is no extremum there. And you can tell so by drawing a sign chart. Next topic. So that was a bit of recap, what we have seen on Monday, and you should try to do the questions on that. So now let's look at functions. So we have already met functions before. We have seen that a function is basically, well, you have some set A and you pick an x in that set. Then you have something that maps that to a point value or some object y in B, and that is a function. So a function takes an x and assigns a b to it. And of course we're always dealing with numbers. So we pick a number x and we get a number y, but it can be more general. And for the discussion now, I would like to make an example where we take as a domain, we take all of you, so the audience of this presentation. The first function that you could assign to it, so this function f here, is how many years old you are, so your age, 18, 19, 20, whatever. And what you see then is that a lot of you here will all be mapped onto the same value there. Which means that you couldn't go back. You couldn't go from y to x, because if I would start with the age of 18 here, there would be many students in the set here on the left that are all being mapped to this value of 18. So, such a map does not have an inverse, it is said. If you would like to also go from y to x, you would need a one-to-one mapping. So what does that mean? Well, it means, for instance, if I would ask you for your mobile phone number, all of you have a different mobile phone number. So if I take you, student, and I map you to your mobile phone number, since that is unique, I can also make this way back. And these types of mappings, where you have a one-to-one mapping for every student, there is a unique mobile phone number, they are much more common than you would think maybe. So another example would be the student identification number that the TUE has given you. So on your student card there is a number, and all of these numbers are unique for the student. So that would be an alternative. The government also has the burger service number, so there's also a digital ID that everybody has in the Netherlands, which is also unique for people, and so on. So there are many examples where you can walk both ways. So what you can do is you can go from x to y, and you can go back from y to x. So we've already seen during this little discussion that you cannot always go back. So this black arrow, this function g, the inverse function, doesn't always exist. So if it exists, so if you can find a function g such that g after f of x, so what it says here, this here, is we're going to start at x, then we're first going to apply f, and then we're going to apply g, and then we are back where we started from. So that is what it says here. So if you can do that, and also the other way around, so you could start at y, use g to get here, and then use f to come back where you came from. So fgy equals y. Then we call g the inverse of f. And this is the notation. So this does not mean f to the power minus 1. It is not 1 over f. It is the inverse. So the notation may be a bit confusing here and can be confused with division, but that's not what it means here. So it's the inverse function. It's what's happening in the picture here. Now, if g is the inverse of f, f is also the inverse of g. They are pairs. F and g are pairs. So f is g inverse. And as I said, not every function has an inverse. Think of student and age. So which functions do have an inverse? Well, we call a function one-to-one. So one-to-one is a mathematical concept, and the definition is that you call a function one-to-one if, well, here is the formula, fa equals fb means a equals b, But what it really means is for every y value there is one x value. So let me draw a little picture. So if you have a function like this, and if I now draw any horizontal line, you see that it only crosses the graph once. And where it crosses the graph, so at this point, this is the x value that belongs to the y value here. So for every y value there is a unique x. If I would draw a picture like this, then you see that depending on where I am, it can be like here, that for one y value there is 1, 2, 3 x values. It crosses the graph of the function 3 times. So if I only give you the y value, there is not a unique x that belongs to it. So what one-to-one means is for every x there is one y, for every y there is one x. That is what one-to-one means. And if you have a one-to-one mapping, it has an inverse. So there's the theorem here. F has an inverse on A, that's equivalent. So this means the two statements to the left and the right of this symbol, they have the same value. If your function has an inverse, then it is one-to-one. If a function is one-to-one, then it has an inverse. So they mean the same thing. These two statements are equivalent. Now let me look at a little example. So, of course, we are interested to find these inverses given a function. So, as an example, so we are being asked to find the inverse of fx is x to the power 3 minus 5. And on R, I have added that because very often you will see that we specify a certain domain where we consider our function. The reason for that will become clear in a second. But this function is nicely defined for every real number. So for every x, I can compute y, I can compute f of x. And basically in this question, it is given that the inverse exists. So we don't have to show that here. So you may now assume that there is such an inverse. And we would like to have the formula for it. Now the way you do that is that you say, well, I'm going to start with y is x to the power 3 minus 5. And with this formula, if you give me an x, it is very easy to compute y. Now I would like to do it the other way around. So I'm going to rewrite this and I'm going to try to write x as a function of y. So try to write x as a function of y. Now here, that's not so difficult. So if you do y plus 5 equals x to the power 3, you see that apparently x is the cubic root of y plus 5. The cubic root is just a fancy way of saying the third root. Or y plus 5, if you like. You can also use this notation to the power 1/3. And this is basically the inverse function. So we have x is g of y equals f inverse y equals y plus 5 to the power 1/3. So now we have achieved what I set as a goal initially. Now if you give me a y value, it is very easy, with a calculator of course, to compute the corresponding x value. So now we have both ways. We can go from x to y, and we can go back from y to x. Now, one more tricky thing, especially if you're doing online questions, the online test or the online practices, sometimes the question is being stated as find f inverse x. Now, that seems a bit strange because we have just found here this formula, and that is in terms of y, but the y here, well, we sort of like to give it a meaning, but really it's just to define the function, right? It's just you give me something, and then the formula to the right here tells you what to do with that something. And that something you can denote with y, x, z, or whatever you like. So if the question that you're being asked is to return f inverse of x, then you could also give it as x plus 5 to the power 1/3. So this just tells you that the symbol, whether you use here a y or an x to describe your function, that is not important. So, but when the system asks you to explicitly give f inverse x, then you have to give this formula. So just replace the y by x. It is not very interesting, but that's something that you should be prepared for. And Florine has a question in the chat box whether you could also take the negative cubic root. That is not true. And the answer to your question, I'm going to do that in green to show that it doesn't belong to this example anymore. The cubic root of 8 equals 2 and not minus 2. Because if you do minus 2 to the power 3, you find minus 8. And if you do 2 to the power 3, you find 8. So it's always for if the number that's in the root, so here it's a 3, there is this distinction between the odd and the even numbers. So if you take the normal root that has 2 or 4 or 6 or 8, then you have to make this distinction. But if you have a odd number here, 1, 3, 5, 7, then there is only one solution. So hopefully this little example helps. And I also recommend you to pick numbers, just like I do here. So if you forgot the rule, the computational rule, the algebraic rule, then just see what happens if you plug in some numbers. That sometimes helps you to remember what it should be like. Okay. Now, just one quick remark before the break. So if you have this function, y is x squared, so a normal parabola, then you see that if you draw a horizontal line here, or as it is suggested in the picture at height 1, you see that there are two x values that correspond to y equals 1. So this function is not 1 to 1, it does not have an inverse. So if you consider this function on the interval from minus 1 to plus 1, or for every real number, it doesn't have an inverse. And you see that indeed if you solve this, then we have basically two solutions here. Now, there is a way to tackle this problem, and that is to just consider the function on part of where it is defined. So if we just look at the function here in the blue box, so that basically means that we take as a domain for the function 0 to 1, then you see that it is 1 to 1, because for every line that I draw here, it only crosses the graph in the area that we are interested once. So there is an inverse, and the inverse is the square root of x. Now, last, I could also have chosen a different domain. So I could also consider the function from minus 1 up to 0, And then you see that indeed it is 1 to 1 again, because if I draw horizontal lines, it only crosses the graph once. And now the inverse is minus square root of x. So apparently it depends on the domain that you consider a function on, whether it has an inverse and what the inverse function is. So for different parts of its domain, it may have different formulas for the inverse functions. So this is a great moment to have a little break. So we'll have a 15-minute break and I'll see you back at 11:45. So let's start again. I hope you had a good break and that you got some coffee or tea. I wanted to make an espresso, but I thought it would be noisy, and then the guy who's making noise in the other house would think that I would be finished and he would start making noise again, so I'll settle for water. I just wanted to say again that before the break we spent quite a bit of time on your questions, and that's perfectly fine with me because the lecture that I have, the slides, I can tell you what is on them and I will do that. But for me, it's more interesting to actually talk about the things that you're having difficulties with. So if you have any difficulties, if you find anything troublesome and you don't understand, please let me know and I'll happily spend time on that. As a bit of a side note too, if you have any ideas whether it is hard for you to concentrate and whether I should do anything more interactive, like I could do Mentimeter questions or stuff like that. Some of my colleagues do that. If you have any ideas about that, would you like that? Would you not like that? Let me know. You can put it in the chat. You can also send me an email. That's also fine with me. But I'm open for suggestions on that. So the current format works for me. Does it work for you? Are you happy with that? Or would you like some interactive questions that you actually have to work and solve a problem that I just told you about? I can do that, but I thought it would not be very inspiring just to pose a mathematical question with 4 multiple choice answers and then see how well you all do. I mean, I can do that, but it takes time and I'm not sure if it adds a lot. So if you have any suggestions from other courses or from high school, please let me know. Having said that, I will continue with the lecture for now. And as you can imagine, a function and its inverse are tightly related. Basically, if you have a function and you know it has an inverse, if you only have this one function, you can immediately compute the inverse in the sense that for every x you can compute a y. And then, well, you can basically make a table or a list of corresponding x and y values. So given a function, you already have all the information you need from the inverse. So what I would like to do now is consider the graph of the inverse functions. So say that you plot the graph of a function f of x, so you plot y as f of x. What does the inverse function look like? Now, to answer that question, let us first consider just one point in the plane. So I have normal x-axis, y-axis, and I have a point P with coordinates a and b. Then if you also draw the green line here, y equals x, and if you mirror the point P in that line, you get Q. And if you think a little bit about that, then you will see that you just swap the coordinates. Basically, you are changing the roles of the x and the y-axis if you mirror in y equals x. So x coordinate becomes y coordinate and vice versa. So if you have the point AB, then if you mirror in that line, you get BA. Now from that, it follows that if you have a function, a red graph like this, y is f of x, and if you mirror that graph in y equals x, then you can find the graph of the inverse function. Now, you can prove that. It's not very difficult, but then again, it's a little bit technical, so I'm not going to do that now. If you're interested, I'll happily spend more time on that. But just for now, if you have the red graph, if you mirror it in y equals x to get the black graph, then you have found the graph of the inverse function. So that helps quite a lot. So if you have a function and you want to know what the inverse looks like, you can just mirror it in y equals x. Okay, that's great. Now, as we have seen a couple of times before, I introduce some mathematical concepts and then we're going to apply them basically. So now I have told you what an inverse function is, and we are going to look at the inverses of functions we know. So functions we know are, for instance, sine, cosine, tangent. So let's look at the sine function. So here's the sine function. You know what it looks like. It crosses the axis at 0 and at pi and at 2 pi, also at minus pi and so on. And it goes between minus 1 and plus 1 all the time. So up here is plus 1 and down here is minus 1. As you can immediately see from this graph, if I draw a horizontal line like this, you see there are many x values that correspond to this function value. So here and here is 1 and here and so on. So it is not one-to-one. So what we have to do if we want to talk about an inverse function, and we want to do that because that is the current topic of this week, and it has many applications, of course, that's a better reason. We have to restrict the function. So we have to choose a domain such that on this domain, the function is unique. So basically, if it starts at minus 1 at the left of the interval, it should go to plus 1 and then we stop. So what we can do, there is many choices, but the standard choice is that you say, well, we're going to start here, and then we're going to consider the sine function up here until it reaches plus 1. Now, as you know, the corresponding x values are minus pi over 2 and pi over 2. So basically, I have put it in blue box here. In this blue box, the sine function is 1-to-1. If I now draw inside this blue box horizontal lines, you see that each of these horizontal lines crosses the graph only once. So the function is 1-to-1 if we consider it on this interval here, and that corresponds to the blue rectangle that I've shown here. So on this interval, the function has an inverse. Now, and since this is so important, because in many technical applications we want to compute angles. And to compute angles, well, normally we draw a little triangle and we have 2 or 3 sides of the triangle. We can compute the angle if we use the inverse sine, because the sine in a rectangle is the opposite side over the length of the hypotenuse, and then we do the arcsine, the inverse sine function, to find the corresponding angle. So the inverse of the sine function is called the arcsine, and we write it in mathematical notation as ARC SIN. And what it means, y is the arcsine of x. That means that the sine of y equals x, so they cancel each other out, they are each other's inverses. But there is this extra requirement, and the extra requirement is due to the blue rectangle in my figure here. Since we consider the sine function on an interval only, we have to make this extra restriction here. So let's see, here it is again. So this is the same blue box. So what you should note is that it is only defined for x values in between minus 1 and plus 1. Because if you look at the sine function, you know that it only reaches minus 1 and plus 1. So you can only have the arcsine of something that is in between minus 1 and plus 1. Then the book uses this notation, and that is a bit confusing, as I already pointed out when we were talking about general inverse functions. So we don't use that. But you will encounter it when you're studying the book. So sine inverse and arcsine are the same. So what we have is that they cancel out. So the sine of the arcsine just gives x back, provided that x is in the domain of all these functions. Similarly, the arcsine of the sine, they cancel each other out, but only in this region. And for the graph, to make the slide complete, this is what you get if you mirror the sine function in y equals x. So here is the arcsine function. So you see it is defined for x values in between minus 1 and plus 1. You also see that the y values being reached are basically the domain where we considered the sine function. So from minus pi over 2 to pi over 2. And there is one extra bit. If you look at the tangent lines here at the left and here at the right, you see that it has a vertical tangent line. So if you would compute the derivative of this function at -1 and +1, x equals -1 and x equals +1, then it's undefined there. And we will see that at the end of today's presentation, or otherwise on Monday if I do not finish, we'll see. So this is the arcsine function. Now, since we have these funny restrictions here, you sometimes see them pop up in exams where we have questions about the domain of these functions. So let's see, here are 2 test questions and I often skip them, but today let's have a look at them. So first, what is the domain of the function arcsine x minus 2 over 3? Now, to do that, you should recall, so let me write that here. So if you have the function f of u equals arcsine of u, the domain is that -1 less or equal u less or equal 1. So this u should be in between these 2 values. So for the function we have here, we have that x minus 2 over 3 should be in between -1 and +1. So you see that apparently -3 less or equal x minus 2 less or equal 3. So apparently if you add 2 to all 3 terms, you see that -1 less or equal x less or equal 5. So the domain is from -1 up to 5, and -1 and 5 are included. Then the second one, so the first question wasn't really using that the arcsine is the inverse function of the sine. It was just considering the domain and leading to an inequality as we have seen in week 1. Here we are being asked for the inverse function of sine squared. So the trick that we did before, y equals sine x squared, apply the arcsine, and for now we're going to assume that we're in the domain and we don't have to worry about that. So arcsine y equals x squared. So x itself is plus or minus the square root arcsine y. And without any additional information, we cannot choose whether we should have the plus or the minus sign here. So this is the inverse function. Okay. So those were 2 small examples, and you will have more questions on this when you are doing the exercises. If we talk about the sine function, then you can already expect, hope, fear that there's also going to be a cosine function, and there is. So here's the cosine function, and the definition of the inverse of the cosine is going to be completely in the same way as we did for the sine function. So first of all, we should consider a domain where the function is 1 to 1. So because it's obviously not here, just draw a straight line and you see that it crosses the function many times. So we want it to go from in between -1 and +1 and only once. Now if you look a little bit, then well, we cannot go both to the left and to the right, because here whenever we draw a horizontal line it's going to cross it twice. So we can start at 0 and then walk along the graph until we reach -1 here. So on this bit, the cosine function is 1 to 1. So let's draw a blue box like we did before. We're going to consider the cosine function from 0 to pi as x values, and the corresponding y values are from -1 to +1. So the function cosine of x is 1 to 1 if we consider it on 0, pi. And the inverse on that specific interval we give a name, and that name is the arc cosine. So y equals arc cosine x, that is equivalent to saying that the cosine of y equals x, and y is from the interval from 0 to pi, because that is the interval we consider the cosine on. Similar slide as I had for the sine and arc sine. So here's the definition again. It is only defined for x values in between -1 and +1, and the book uses cosine -1x, cosine inverse x. And we have these cancelling relations. Cosine of the arc cosine, they cancel out, provided that x is in between -1 and +1. And also arc cosine and cosine cancel out, provided x is from 0 to pi. We can look at the graph, and the graph is the cosine function mirrored in y equals x. And you see that it's quite similar to the arc sine. I mean, it's not identical. So it is also defined on the interval from -1 to +1. And you see that it has a vertical tangent line at the two endpoints too. Okay. Sine, cosine, tangent. The tangent function, it goes similar, but it is a little bit different from the twos we had. Because as you see here, well, it is obviously not 1 to 1, but if we consider this bit of the function here, then you see there it is 1 to 1. So we are going to consider the tangent of the interval from -pi/2 to pi/2, endpoints excluded, because the tangent is not defined at the two endpoints. So this is the arctangent. So y equals arctangent x, means that tangent y equals x, and y is from this chosen interval. The interesting bit now is that the arctangent is defined for every x value. So because the tangent itself goes from -infinity to +infinity, you can find, let me draw it, that's easier to say. So you see that if you mirror it, that this goes all the way to -infinity and this goes all the way to +infinity. Additionally, what you also see is that the function has horizontal asymptotes. So this is a horizontal asymptote and this is a horizontal asymptote for x going to plus and minus infinity. Okay, and the book has a different notation, of course. So now, if you do the tangent of the arctangent, that will always be x. Every single x that you take, that will always hold. Okay. Let me check what I wanted to show you more. Since these functions, sine, tangent, arctangent, and so on, they're all related to each other, and sometimes you can use a little trick to simplify expressions. And I want to give you an example here, and you will have some questions on it, but then you know what to do there. So it says, so what we have basically seen is that the sine of the arcsine, well, they cancel out. So you could ask yourself the question, if you now take the sine of the arc cosine, so if you mix them, can you also simplify these expressions? And you can. And the way you do it is like this. So say that we want to have a simpler expression for sine of the arc cosine of x. So the trick to do that is that you say, well, I'm going to write this as sine of phi, and phi I'm going to choose as arc cosine x. So I didn't do anything, right? So I have f of x is the sine of the arc cosine x. And I just say, well, this is sine of phi. with phi equals arc cosine x. So I just introduced a new letter. But there is a nice thing, because now I have, forgetting what we did before, I have phi equals arc cosine x. So that is the same as cosine phi equals x, because arc cosine, they're each other's inverses. So I can rewrite that, and then I have cosine phi equals x. Now I'm going to create a triangle with an angle phi here and a 90-degree angle. And now I know that cosine phi equals x. That is the length of the adjacent side over the hypotenuse. So I'm going to give them lengths x and 1, because if I do that, I can choose that. I have a bit of freedom here. But I'm going to say one is x, the other is 1, and then the cosine fits. Now I can use Pythagoras to compute this length, square root 1 minus x squared. And now something interesting happens, because the original question was to find the sine of phi. Now here I have a very nice triangle where I can read off the sine, because the sine is the length of the opposite side, this one, divided by the long side, this one. So apparently the sine of phi equals the square root of 1 minus x squared. So apparently I can write f of x as the square root of 1 minus x squared. So a lot of magic going on here, but the original question was, we have this here, f of x is sine arc cosine x, can I write that simpler? And the answer is yes, you can. It is the square root of 1 minus x squared. And to get there, I used these relations from inverse functions, and I drew a little triangle. So try to do a couple of questions with them, and if you do not manage, let me know. So last bit is a little bit on basically coupling these things we've seen now. So as you may recall, we started this week by looking at differentiation. Now we have looked at inverse functions, and I told you that inverse functions are closely related to their original function. So if you have f and f inverse, they're tightly related. Then you might wonder, can I also use that for the derivative? So is f prime also related to f inverse prime, to the derivative of f inverse? And it is. So let's have a look. So that is the derivative of the inverse function, and in the book you will find this in 2.5. So let f and g be inverses. That's a bit easier to write than f and f inverse, especially if we talk about differentiation. So f is g inverse, and then automatically g is f inverse. So we have this relation, f gx equals x. Can I find the relation between f prime and g prime? Now what I'm going to do is I'm going to differentiate both sides of the equation. So if I differentiate x, so I do the d dx, differentiation of x, well, that's just 1, right? If you differentiate x, you find 1. The slope of y equals x is 1. If you differentiate the left-hand side, well, that's the d dx of f g x. I have to use the chain rule here. So that is f prime gx. But then I'm not done yet, because I have to add times g prime x. And here you see that indeed there is a relation between these two derivatives, because apparently, with what we have just found, the f prime gx times g prime x equals 1. And now the tricky bit here, and that's going to lead to quite a bit of confusion, I can already predict, is that here we have the derivative of f prime. Here we have the derivative of g prime. That's great. So there's a relation between these two. But this one is evaluated, has as an argument we consider at the point gx, and this one we consider at x. So we do have two derivatives, but at different points. So along different positions on the horizontal axis, if you like, if you would plot them. Okay. So let's see how this works. I'm going to do an example in a second. So this is what I just did, handwritten and then typed. So what we have is this theorem. So we just we solve this for g prime, and then we find g prime x is 1 over f prime gx, which is 1 over f prime y if we just label y equals gx. So they're in different points here. Let's look at an example, and that hopefully makes clear what's going on here. So let's consider the function x to the power 5 plus 3x to the power 3 plus 2x plus 1. And it's given that f has an inverse, so we don't have to show that. So the question is, what is g prime at 7? Now, if you just look at this question, you might be tempted to try and find the function g. So how did we do that? Well, then we would say that y equals x to the power 5 plus 3x to the power 3 plus 2x plus 1. And then I would have to write x as a function of y. And you can probably imagine that's not so easy here, if at all possible. I don't think it is possible. So that is complicated. So we cannot first find the function g and then differentiate it. We will have to use the relation between g prime and f prime in order to solve this question. So let's see. So it's hard to find g, so I'm going to use this relation. So this is just copied from the previous slide. Now, I am being asked for g prime at 7, so x should equal 7. I find that by computing f prime, and I need f prime at gx, which is g7. So I need the g of 7. So let's say that g of 7 equals y, as we did up here. Now I'm going to apply the inverse to both sides of the equation. So I'm going to say f of g of x equals f of y. F and g are each other's inverses, so they cancel. And I was interested in x equals 7. So what I need to try and find is a number y that if I apply f to it, if I compute f of y, that it gives me 7. So I have to look at the formula for f, and I have to try and find for which number do you get 7. Now, you realize that it should be a nice number. It should be able to find this using trial and error. So if you do that, you should always try. So let me go up again. Try simple choices for y. For instance, y equals 0, y equals 1, y equals minus 1, y equals 2, y equals minus 2, and probably it's among those. So here, let's see, what do we have? If you take y equals 1, then we get 1 plus 3 plus 2 plus 1 equals 7. So this is the tricky bit. So we want to use this formula here from the previous slide, but we have to do this conversion between these 2 points. So basically what we have done now, if I summarize, we have found that x equals 7 corresponds with y equals 1. And if you go this way, this is f. And if you go, let's do that in black, otherwise you cannot read it. If we go this way, it is the function g. So they're each other's inverses, and axis 7 is linked to y equals 1 by these functions. Okay, so now let's solve the question, because this was only like the introductory bit, and for this question, I guess the most difficult one. So we want to use this formula, and we need this little transformation in between the 2 points. So what I'm going to do is we need f prime x, and we need this y value. So the y value, we just covered that. So to find f prime x, well, that's easy, just differentiation. If you differentiate this thing, you find this expression. That's easy. And then if y equals g of 7 and they're each other's inverses, then with what we have just seen, we have found that y should be 1. So here I have called it trial and error. And then we're basically done now, because now we can just apply the formula. So the g prime of 7 is 1 over f prime in the corresponding point, which happens to be 1. So 1 over f prime 1. Well, we have computed f prime, so we can easily substitute x equals 1 there, and then we have 1 over 16. So that's how this works. That's how this link is between f, its inverse, and the derivatives. So if you have f and g and their inverses, there is a relation between f prime and g prime, but it's a little bit complicated. And the little bit complicated is basically this part here. So try to do a couple of questions with that. If you do not understand, let me know, and I'll get back to this on Monday. So the last topic for today is implicit differentiation. So we're still talking about differentiation, and this is also kind of linked to inverse functions. So say here we have a circle in 2D with center 0, 0, so around the origin, and radius 2. Now, as you know, the corresponding equation is x squared plus y squared equals 4. That's a circle in 2D. And this 4 here is the radius squared, so the radius itself is 2. And this point, you can easily check if you compute x squared plus y squared is on the circle. And the question is, if you have the tangent line, what is the slope of the tangent line at that point? Now there's 2 ways you can do this. The first way is something that you could already do, that you already know how to do, which is solve the equation for x squared plus y squared equals 4 and differentiate. Did I put that on the slide here? No, I did not put it on the slide. So let's see how that works. So we have y squared equals 4 minus x squared. Y itself is plus or minus the square root 4 minus x squared. Now, which one do we need? Well, p equals 1 comma minus square root of 3 is the point, so should be on the curve, should be on the graph. So apparently we have to take y equals minus square root 4 minus x squared. If you think a little bit about this, then you will easily see that if you look at the top part of my circle, so the top bit here, this bit, the green bit, is y equals plus 4 minus x squared. And the bottom bit, that's still in red here, is y equals minus square root 4 minus x squared. So we can describe the circle using a formula in terms of y, but we need two of them, one for the top half, one for the bottom half. Well, and this thing you can just differentiate, right? Then you find dy dx equals minus 1 over 2 times the square root times minus 2x. So here we have found the derivative. We can plug in x equals 1 and then we know the value. So what you would find here, if you compute this for x equals 1, so dy dx for x equals 1, what you would find here is 1 over square root of 3. Okay, so that's the slope. Now, that's one way to do it. There is one more way, which is called implicit differentiation. And what you do is you do not do this, so you do not solve for y. You look at this equation and you differentiate the equation. So it works like this. So we assume that we can write y as a function of x, and then we do not solve for it, but we just plug that in. So I replace y by f of x, and then I differentiate this equation. So if you differentiate that, if you do the ddx of x squared, well, of course that's 2x. And if you do the ddx of fx squared, so this term here, you differentiate, what you find is 2 times f of x. And then with the chain rule, and that is important, you get an additional f prime of x. So then you find the formula that's here in the black box. And now you can plug in x equals 1, because that is the point we're interested in. And if you do that, if you plug in x equals 1, you find, so from this equation, I plug in x equals 1 and I find 2 plus 2 times f of x. Well, f of x, we're in the point minus square root of 3. And then we have here f prime 1 equals 0. And f prime 1, that's the slope of the tangent line. That is what I would like to compute here. So we see that f prime 1 equals 1 over square root of 3, which is, of course, exactly the same as what we found using method 1. That should be true, right? If you have two different methods, they should give the same result. But here, the advantage, it may look a little bit more complicated here, But the advantage is that we do not have to solve the equation for y. So here we do not have to find y as a function of x. So that can help quite a bit. And you will see a number of examples with that, and it's called implicit differentiation because you do not have an explicit formula for y. So if you would write y as a function of x, really solve for it, that is an explicit formulation. If you just have an equation like we have here, that is called an implicit relation, and hence it's called implicit differentiation. So here are two more examples. So this is what you should do always. You replace y by f of x and you differentiate the whole equation, and then you solve for f prime of x. And here are two questions where you can do that. So I'm not going to do them now. Try to solve them yourself. And then if you do not manage, let me know and I'll get back to it on Monday. Now, using implicit differentiation, you can find the derivatives of arcsine, arccosine, and arctangent. I can't show that. I'm not sure if it adds a lot of information, so I'm not going to show that here. I can do, but I think A, that you have seen these derivatives before, and B, they're provided as in the formula sheet that you will get during the exams. If you've already taken a look there is a list of integrals. So basically the inverse ones, so the integral of right-hand side equals left-hand side, they're on the exam paper, so you don't even have to know them by heart. So that wraps up the presentation for today. So quite a busy week again, as you see, but basically split into two parts. We've been looking at derivatives and how to find maxima and minima. We've seen that you can find quite some neat examples there, like the beer can and the area that you can optimize. And today we looked at inverse functions, and we have looked at specifically arcsine, arccosine, arctangent, and a little bit more on differentiation. So that wraps up the week 4 material. As you know, next week, week 5, we have new theory. There will also be the midterm test. You will get more information on that. The topics for the midterm are weeks 1 up to 3. So week 4 is not in the midterm. It was not listed correctly on Canvas before, but the midterm is about week 1, 2, and 3. Look at the old exams. Look at the information you get, and I wish you a great week, and I hope to see you again on Monday. Bye for now.